Yeah, so I'll talk to you about real-time patterns. So something that a lot of us are using. Usually when we have real-time patterns, this is how they look. Let's examine, for example, pattern A, B, and C, which both start here. Can I change it to a laser so you can see better? Start up here and go all the way down here. All of those patterns are enriched in the lights and depleted in the heavies, but they're different. For example, pattern A goes steep down, then flat. B starts flat, then it goes down, and pattern C kind of goes down and then up again and then down. And usually the numbers or the parameters we use to represent that, for example, lanthanum over lutetium, will tell you that it's overall blood reference rich, but it will not tell you much about what happens in between. To do that, you will need another parameter. For example, what some people do is combine those with the ratio of the elements at the extreme ends with something in the middle. For example, you can have a lanthanum over lutetium and then lanthanum over samarium. And then by looking at those two numbers, it gives some kind of indication on what's the curvature. The problem with that, it's not independent of the others, because if we take this pattern of how might a garnet look like, so we have some numbers, and you see it has some kind of curvature, it's kind of convex upwards, right? If we take this other pattern, which has exactly the same curvature, because this is how we made it, except that it's kind of rotated to the other side, those numbers change. Now, this number is greater than what we had here, and this has changed in order of magnitude. So those numbers may be useful in one case, but it's very hard to generalize from them to kind of the entire universe of possible rare-thermal patterns. The other problem is that when we're looking at things like serum and europium anomaly, so here's how a zircon might look like, and I started at terbium here, it doesn't go all the way. And something that we really care about in zircons is serum and europium anomalies. The way we usually do it, we take a measured value, which is up here, and we ratio it to what we would expect there to be based on the interpolation between two different elements. So we take lanthanum, we take praseodymium, we connect them with a straight line, and then we ratio what we measure to this. The problem is that the pattern is curved. It's not a straight line. And in this case, you can see that where the pattern should actually be, had there been no redox effects, is in this dot here. Now, it doesn't look like a lot of difference, but this is only because we're looking at the zircon. It's a log scale plot covering 6 orders of magnitude. So the difference in the number you get for the serum anomaly between using the interpolated line and the actually where it should be is about 20%, which is actually a lot. The way to solve all of those problems, one, that those numbers don't give you all of the information, B, they're not independent, and C, they're actually not that accurate, is by using something that we call the lambda method. Now, I'll just show you exactly how it works. So I made an online app, which is available here. In this place, I can go to Google my name, you get here, and then it has links in here. And it allows you to see what the lambdas are, okay? So we can set it to 0, and then we have all kinds of lambdas, lambda 1, lambda 2, lambda 3. What those mean is lambda 0 is just the up and down, where a pattern goes in terms of average abundance. We can have lambda 1, which is the linear slope. So it can go this way by having a number, for example, 22, or we can have a negative one, which goes the other way. We can combine it with things like curvature. Let's make a number here. We can also get rid of that. And then this number, which tells us what the curvature is independent of the slope, whether it goes this way or that way. Lambda 3 is this kind of sinusoidality. So I can just get rid of this. And this is a look. And with all of those, you can kind of construct your own rare-thermal patterns. It has some preset ones you can play with. Here's one, for example, how it might look like, and the lambdas that make it. Now, this is going from lambda to lambdas to patterns. What you usually care about is when you have data that you measured in your work, and you want to know what the lambdas are, so you can look for all kinds of patterns and trends in the data. For this, we have the other app, which is called BLambdaR. Again, same website, and you can just go and Google me, and the link is here. What it does, it takes real-time data. So when you just open it, it has kind of preset patterns in it you can play with. The numbers down here, that's the ppm value. Those are the numbers that you can get from your laser or ICP or assays or whatever. There are instructions. It's all open now, free for anyone. You can just go there, read the instructions, and upload your own data. And what it does, it decomposes data into those numbers. So for example, if you look at this pattern, for example, the circles here, that's the actual measured data. The solid line is the fit. So decomposing that into a polynomial, which is the shape of the pattern, and you can download the results here, and it gives you all of the lambdas: lambda 0, lambda 1, lambda 2, lambda 3. And if you don't remember what the lambdas mean, don't worry, you can just take them, plug them into LambdaR, and it will show you exactly what they are. For example, lambda 3 is -107. You can just go lambda 3 -107, sorry, and it shows you that this gives you this kind of curvature, okay? And you can combine them and see what they actually mean and how they change. Now, what is this good for? So I'll show you an example. So we've seen this. Here are some real-time patterns for all deposits in the Mount Isa region. We have a bunch of scans, we have a bunch of IOCGs, and we would like to know whether there are any trends or relationships between them that we can see or think about or use somehow to understand the system. When you plot all of them together, it's a huge mess. It's very hard to see what is happening here. Again, you can go back to things like lanthanum over lutetium or all of those, but they will not tell you much about what's happening in between, because this one kind of goes flat and then steep. This is steep and then flat. You don't really get to see that. Now you can split them if you want. It makes it easier to see, but then you start losing the relationships between all of them, because if you look at scan 3, it kind of looks maybe a bit similar to IOCG 1, but is there a relationship? How do they plot like in the big picture? So what you can do, you can take your lambdas that you download from the app and plot those, and then you get stuff that looks like that. So what I'm plotting here is lambda 1, lambda 2, lambda 1, lambda 3, lambda 2, lambda 3. So it's pretty much all the possibilities, also with the European anomalies calculated from the app, by the way, so more accurate than how you would usually do it by interpolating samarium and gadolinium. And when you look at that, you can see all kinds of trends. So for example, in this plot, you see that all of the scans plot on the straight line that goes to the origin of where the IOCGs go, right? I mean, it's not perfect here, but you do see this trend. If you look at the one with the European anomalies, that's actually perfect. Right? You see this and this, so all of the scans are here, all of the IOCGs are here, and they have some kind of joint origin. Same thing on the lambda 3 plot, right? You have this thing here, so it gives you an option to think about something. Well, maybe there's a process, maybe there's something that links them. Once you see that, you can start thinking about kind of a petrogenetic process. You can plot instead of lambdas, you can plot average copper grade or average cobalt grade. Now, again, this is data. It doesn't have to be lambdas. If you're looking at weathering laterites, you can do a lambda 2 and mean annual precipitation. I mean, you can do all kinds of things to see patterns that you would otherwise not be able to see at all in your data. That's about it. It's if you think that this is interesting, then you can just go to the app now and upload your own data and see how it looks. You can contact me, email me, find me on LinkedIn, whatever. I'll be happy to help you think about what you can do with this and how this is useful. And there are several papers about that topic, open access. So me and Morgan, who will speak later, if you want them, you can also email me and I'll send them to you. Okay, so that's it. And thank you.